revealed by laboratory earthquakes. This is the work that I've carried out over the last few years at Caltech. And I would like to acknowledge my main co-authors for this study, Professor Aris Rosakis and Professor Nadia Lapusta at Caltech. And I've recently moved to École Centrale. Okay, so let me get started here. First of all, we all know that earthquakes occur as dynamic frictional ruptures along pre-existing faults in the Earth's crust, and numerical simulations as well as seismic inversions have advanced our understanding of the earthquake process. However, they are both based on assumptions that may or may not be satisfied in real case scenarios. So that's one point. Another point is that friction is a key ingredient, both in the numerical simulations that are used to understand earthquakes and in the physics that controls how rupture propagates and how ruptures unzip faults in the Earth's crust and release waves that cause destructive shaking. And yet friction is one of the least constrained variables in earthquake mechanics. So these reality, and so let me point out here, I've got numerical simulations taken from the Lapusta's group, where, in the bottom panels, you can see some interesting nucleation and post-seismic rupture behavior, but numerical simulations can use a variety of fault rheology and can study a range of possible combinations, as you can see in the top panels on the right-hand side. However, what the real rheology is unknown, and so this reality highlights the need for well-instrumented laboratory experiments that can reproduce the basic physics that controls rupture dynamics, while at the same time maintaining enough simplicity so that clear conclusions can be made. In this presentation, I would like to start by describing our experimental approach and how our experimental approach can be used to study the force field behavior of dynamic ruptures and unravel the underlying friction behavior for cases of constant stresses, and then revisit both the full field behavior and the friction evolution in cases when the normal stress is not constant, mostly for analog materials. And then I would like to step up to cases where we include some natural quartz material along the interface, and then study friction evolution due to the presence of gouge. Right, so let me show you the laboratory setup. The key ingredient is the specimen here, loaded in this press. Let me highlight it. The specimen is loaded uniaxially by a load P, which then produces a normal and shear level of pre-stresses along the inclined fault, which is cut along this inclined interface between two plates of analog material, which typically is either homalite or PMMA, so plexiglass. Ruptures are nucleated by the small bars of a nickel chrome wire placed across the interface, but once they are nucleated, ruptures develop spontaneously under the level of applied pre-stress. And then we focus on an area of the specimen where a high-speed camera here looks and can take images at a speed of up to 10 million frames per second. So naturally, when we scale down earthquakes from the size of kilometers to the size of millimeters, we also reduce the timescales from seconds to microseconds, and therefore we need an ultra-high-speed camera to capture the process. And I will explain in a minute how the acquisition works. Then we also have laser velocimeters that can capture accurately the evolution of the temporal evolution of particle velocities, and strain gauges, which can be deployed in selected configurations. Not shown here though. Okay, so first of all, how do we make earthquakes in the laboratory, and why do we normally use analog materials? The main reason is due to the nucleation length scale, which is the critical length scale over which a fault needs to slip in order for instabilities to develop. And so this nucleation length scale is depends on a number of frictional parameters that are here. It depends, it is inversely proportional to the effective normal stress. So once you set the interface parameters and the level of normal stress, it depends on the shear modulus of the material. And it turns out that for rocks, the shear modulus is 25 times larger than for typical analog material, such as PMMA. And therefore, the nucleation length scale is 25 times larger. And this is the reason why we prefer to have analog materials, so that we can have like small specimens. Now, people nonetheless, people use rocks in several setups. This is an example of a setup at USGS. You can see the diagonal here is 2 meters long. Of course, it has the advantage that this is a natural material, but the disadvantage that it's a little bit cumbersome to operate. This is another version developed still with rock samples with a scale of about 1 meter here. It's 3 meters long, developed by Greg McCluskey at Cornell. And then there are setups with analog materials. So there are various versions around the world. On the left-hand side is the well-known setup by Jay Feinberg and co-workers. And on the right-hand side, there is another version, well, a different version by Latour, by Somaya Latour, who uses photoelasticity to capture rupture nucleation and behavior. And there is also this other version by Marie Violet at EPFL and co-workers that uses strain gauges and accelerometers. So in a nutshell, various setups have various advantages and disadvantages. So one key feature about our setup is the capability of measuring the full field characteristics of dynamic ruptures. And so the method is based on digital image correlation. Now, for those of you who are not familiar with the method, the main idea is that a sequence of images is captured by a high-speed camera. The surface of the specimen is decorated by a black and white speckled patterns that confers a characteristic gray level texture to the images. And then a reference images can be compared and correlated to subsequent deformed images in order to infer pixel by pixel the displacement field. And so here we can put an example of the interface parallel and interface normal components of displacements. So for you to get used to this type of motion, and now this is an example for a supershear rupture. Let me show you that, let me point out that, so the fault parallel component is kind of as expected in the sense that it has this motion in the fault parallel direction, so as expected for a mode 2 rupture. However, as the rupture propagates along the fault, it also moves in the direction perpendicular to the fault, as you can see in the panels at the bottom. So we can use then these displacement fields to differentiate them in time and in space in order to get particle velocities and strains. And then we can use the constitutive linear elastic properties of the analog material in order to obtain the stress components and then friction from that. So now let me focus on the spatio-temporal characteristics of dynamic ruptures. Now, studying dynamic ruptures is, of course, important because many earthquakes propagate at sub-Rayleigh speeds. So it's important to understand the characteristic of sub-Rayleigh ruptures. Less frequently, earthquakes propagate superficial speeds, but when they do so, they are more damaging. So it's important also to understand these characteristics. So in the past, using this setup in the group of Professor Safkis, it was possible to show that ruptures could indeed propagate at super shear speed using dynamic photoelasticity. However, this approach was semi-quantitative, so it did not allow to quantify particle velocities and stresses at every point along the field. So this kind of prompted us to develop a different approach, and this is the image composition approach. Now, I'd like to show you a sequence of images obtained during the propagation of a sub-Rayleigh rupture. The panels showed here indicate the particle velocity in the fault parallel and fault normal direction on the left and right-hand side, respectively. The scale is in meters per second, and the panels at the bottom indicate the same quantity plotted along the interface. So now, as you can see that the rupture enters the field of view and it propagates through, and also there is a component in the normal direction, and if you can see here the time in microseconds, so it's about tens of microseconds for the rupture to propagate. If we fix on a snapshot, we can see here the rupture tip, and then we can see some compressive and dilatational lobes extending ahead of the rupture tip. And then this pronounced motion in the fault normal direction. Now, for super shear rupture, what we see is something slightly different. So here is the rupture moving along the interface. If we fix a snapshot, we can see that the dilatational and compressive lobes are actually behind the rupture tip, and the rupture, as the rupture is exceeding the shear wave speed, and it forms this Mach cone, which becomes even more visible if we zoom out and see the the far field properties. Now, the fault normal velocity also has some interesting features, but it is less pronounced compared to the fault parallel velocity compared to the sub-Rayleigh case. So if we want to put the two cases next to each other and track the velocity magnitude for a point which is located here, and track the time history at the bottom with sub-Rayleigh on the left-hand side and super shear on the right-hand side, we see that as the rupture approaches this location, we have a pronounced motion in the fault normal direction, which is more important than the fault parallel component. However, for a super shear rupture, as the rupture comes through, we can see that the fault parallel component is more important. And of course, this has implication for ground motion and for earthquake hazard assessment. Now, just as a curiosity, as a side note, the reason how we started off with this type of research is because people use digital image correlation to observe earthquakes from satellite images. They normally do it with images taken just before and after an earthquake, because it's difficult to take images during. But one of the first projects I started working on when I was at Caltech, also in collaboration with Jean-Philippe Awak, was see whether it was possible to actually capture earthquakes real time while they were occurring using a geostationary satellite, which could be appropriately triggered when an earthquake was going on. And then apply these optical techniques in order to study the earthquake process up close. This project was also in collaboration with NASA JPL, and so there was a counterpart looking at the actually optical specification of the geostationary satellite. And so this proved the feasibility of this idea. Now, whether NASA is going to do it or not, it depends on other priorities. But anyways, having developed this technique was good enough to just per se to study a lot of features that is not possible with other technique. So let me now focus on one of the most interesting features, the evolution of dynamic friction. Characterizing friction, of course, is important because friction controls a number of key characteristics in earthquake mechanics, including energy partitioning, rupture modes, stress levels on faults, and more. So this approach is different from classical methods because classical friction experiments, because we don't impose the slip rate history, but we observe friction evolution during the spontaneous propagation of ruptures. So we observe here the shear stress propagating along the interface. Scale here is in MPa. And now if we fix just a snapshot, so this pinky color is about the 10 MPa, which is the pre-stress level. And then as the rupture arrives, shear stress goes up. And then, as you can also see in the plot at the bottom, where we trace the shear stress along the interface, and the stress goes up to a peak level, and then it drops down to a residual level. We can also track the time history of the shear stress at a given point along the interface, and we can do the same for the normal stress. And then we can compute the ratio and plot the ratio of shear and normal stress with key quantities, such as, for example, slip. So if we do that, what we see is the following. So we see that friction increases and then decays nearly linearly up to a residual level, and then it stays nearly constant. So the interesting thing is that this behavior has resemblances with the so-called linear slip weakening, where we have a peak friction, we have a characteristic slip distance, and then we have a residual dynamic friction. And this model, of course, has been used for decades in numerical simulations and to understand earthquakes. So this experiment was done at a characteristic level of shear loading, and we can produce other experiments with different levels of loading. This is an experiment with a much lower loading, which produces qualitatively the same slip rate time history, but quantitatively very different. And so now, if this was the linear slip weakening was an operating law, we would have curves collapsing on each other because they would all be characterized by the same dynamic friction coefficient and characteristic slip distance. However, what we see is something different, as we would expect, because the slip rate is controlling the process. So with a substantially different slip rate, we obtain a different characteristic slip distance and a different dynamic friction coefficient. So another important observation here is that the energy release rate, which is really fracture energy, which is the area under the curve here, is substantially different for these two different curves. So it's the analogy to fracture fracture mechanics really breaks down here. Now if we plot slip rate with friction with slip rates, then we see a pronounced dependence and of course a substantially different behavior for the two cases with different slip rate history. So now, to interpret this, we can start using rate and state friction. Well, most of you here know about rate and state, but for those of you who don't, in rate and state, friction depends logarithmically on the rate and state, and the rate of sliding and the state variable, which accounts for the previous history. Now, normally the state variable is given by an evolutionary law. And this is an example. This is called aging law, but there are various others that can be used. And rate and state friction can be used to explain, there are empirically derived laws, and they can be used to explain a number of basic experiments. For example, they can explain the so-called velocity jump experiments, where, for example, if you slide at a constant velocity v1 and you go to a higher velocity v2, you normally have an increase in friction, and then you have an evolution to a steady state. And then depending whether the resulting steady state friction is higher or lower, you have velocity strengthening or velocity weakening behavior. And then rate and state friction can also result into an effective linear slip weakening behavior. And at a steady state, it depends only on velocity, according to logarithmically, according to this expression. So now we can use.
And Andreen, why don't you go ahead and ask? Because maybe Vito doesn't see.
Yeah, you don't see. So please go ahead.
Thanks, Chris. Great talk so far, Vito. Really impressive. These are all observations, not models, right? Because they're so clean, they look like models.
No. It's all observations. Yes, the full field.
Incredible.
Yeah.
My actual question is, how do you go from these deformation observations to friction? How do you actually measure friction?
Okay, from what we measure are displacements. So then you get strains by spatial differentiation, and then to stress is using constitutive properties. And then by looking at the stress along the interface, because we can measure pixel by pixel, so we have like a line of pixels right on the interface, by taking the ratio of shear and normal stresses right on the interface, and then we get friction.
And do you then need, for the constitutive parameters, do you need to assume homogeneity or? Well,
we basically use linear, so you don't need to assume homogeneity, but we assume a linear elastic constitutive properties. These materials are in large, linear. Now, one feature that one behavior to display these analog materials that they are rate dependent. So if you use an effective linear elastic behavior, you need to account for the high strain rate properties. Okay, so what we do is that we take like a dynamic level of Young's and shear modulus, and we use those to obtain stresses from strain.
Thank you.
Okay, thanks. Okay, so please feel free to interrupt because I may not see your raised hand as I talk. Okay, so
Vito, excuse me, sorry. Hey, one question before you continue. Your experiments, you have two free surfaces on either side of the
yes.
of your PMMA block,
yes.
And that dimension is shorter than relative to the other ones. Is that correct?
No. So the interface is such as that on the top and bottom you have it's the same length of material, so there is no dissimilarity. It's a symmetric interface.
No, I'm talking about the dimension, the transverse one going into, say, into the page of your presentation.
Okay, the thickness.
Yeah, the width. Yeah.
Yeah. So that's that's 10 millimeter width against a 200 millimeter width of the specimen.
And does that have any effect on how the rupture propagates? Does that kind of define directness of the direction where it propagates and how and all the physics that come with it?
Okay, so that's a good question. So by and large, it doesn't change the dramatically rupture characteristics in terms of bilateral propagation, in terms of rupture speed or mode. However, and also the behavior does not change so much on the outer surface where we observe things. But what changes is that if you look inside, because when we are on the surface, so we have surface measurements, so we can only measure what happens right on the surface. Now, if you have a thicker specimen, then so basically on the outer surface, what you have is plane stress like stress state. It's not really that it's plane stress, but it's the out of plane stress is zero, and so out of plane shear stress components are zero, like in plane stress. But as you move inside, towards the interior of the specimen, then you develop plane strain characteristics. So if you have a thicker specimen, then you can develop more, plane strain conditions. Whereas if you have a thinner specimen, it's more like it may tend to reach plane stress, but it may not just make it. So in other words, what changes is what is in the interior, but on the outer surface, it's basically the same.
Okay, thank you. Just one more question. I'm sorry to interrupt so long. Does that also have an effect on the dilation in the direction normal to the fault plane?
Well, yes, of course. It is so in the out of plane displacement. Yes, it would affect the out of plane displacement. Sure.
Okay, yeah, that's fine. So
And we have a set of other experiments that were done before me, to show the effect of thickness. And also we have done numerical simulations, finite element 3D simulations in collaboration with Gianfranco Molinari to show the thickness effect and to study how the stress state changes as you go in the interior.
Okay, thanks.
Okay, okay, let me where were we? Okay, so then in order to see whether rate state can capture behavior, then we can analyze the steady state behavior. And in this diagram where we have steady state friction on the vertical axis and steady state slip velocity on the x-axis. And so the idea is that we take these measurements right here at steady state. So we don't account for the full evolution. We'll do that later. But right now, we just want to concentrate on the steady state. Is kind of the first step we can do. And we place here this cloud of points in this steady state plot. Okay, so from these two locations. And then we add more measurements that are obtained at different loading levels. With this technique, with this set of experiments, and also other experiments obtained by traditional velocity jump tests in a double direct shear apparatus. These two tests were obtained in collaboration with Kilgore and Bieler a while ago, and so we can use these low velocity tests in order to get the rate and state properties, and then see whether the rate and state curve can predict our measurements. And it turns out it doesn't, because there is more pronounced weakening than that predicted by rate and state. So we can add some more weakening using other laws, and one candidate friction law that can do that is flash heating. In flash heating, what happens is that once the slip velocity exceeds a certain threshold VW, then contacting asperities heat up and weaken, and they weaken with the 1/v strength. So that basically it's not logarithmic, it's 1/v, so it's much more pronounced weakening. Now, interestingly, flash heating was initially developed in the context of metal tribology by Mike Ashby and Alain Molinari and co-workers. And then was later picked up by Rice, Bieler, Tallis, and Galsby, and others, and introduced into the earthquake mechanics friction. So if we, now, another point is that we can take this constant friction here, this F0, and we can take it to be the rate and state, so that we can link the rate and state with the flash heating, like so. And we also have here a state variable. And at steady state, we have this evolution. So now we can use the steady state version first of flash heating to see whether, and use the rate and state parameters at low velocity, so that the two models overlap. Rate and state, a combined rate and state with flash heating, overlap at a low slip velocity, but diverge at a high slip velocity, where the flash heating gives a more pronounced weakening. And the point is see whether the flash heating can actually predict the, or is consistent with our pronounced weakening. And so if we do that, then we see that indeed our measurements are consistent with the flash heating law. And this is a good indication that this may be an operating mechanism. Now, it's interesting to compare our measurements with those obtained by Galsby and Tallis on quartzite. Now, note that the horizontal scale here is very different, because in the plot on the right-hand side, we only go up to 10 to the minus 3, whereas we go here all the way to the 10 to the minus 9, because we have this rate and state measurement, whereas these measurements mostly concentrate on flash heating. But nonetheless, there is a qualitative resemblance, which is a good indication of this being an operating law. Now, one important difference, though, is that in the measurements on the right-hand side, so they are obtained with a rotary shear apparatus, where the slip velocity history is actually imposed, whereas here we don't impose it, but we let the slip velocity evolve spontaneously. And also the measurements on the right-hand side are obtained in the far field, and then they are inferred from load cells, and then they are inferred at the interface, whereas here the measurements are right on the interface. So now next step is look at the entire evolution. So not steady state, but we take the actual law, and the game here is take some constraints for the rate and state parameters obtained at low slip velocities, and then use the flash sheeting parameters, or FW and VW, constrained from the steady state analysis that we just did, and then try to see whether we can fit for A and L here of this law in order to capture the full evolution of friction. So, and the input in this law is the measured slip velocity and the state evolution that is derived using this V as input and L as a fitting parameter. And then once we do this, so we have this friction law playing with these inputs, then we can plot an evolution of friction, and we can compare that with the one independently measured and see how they do compare to each other. So these, the black curves here are indicate friction plotted versus slip and versus slip rate for a given loading case. And so this is just the measurement. Now, if we use rate and state friction law with the velocity as an input, we cannot predict the observed weakening. However, if we include flash sheeting, then we can see that we can capture pretty well the measured behavior. So this is another indication that flash sheeting may be indeed the law controlling this process. So now let me switch on to the case when the normal stress is not constant. So this piece of work has been done in collaboration also with Yuval Tal, who used to be at Caltech and now is at Ben Gurion University in Israel. And the main question we want to address here is whether the shear resistance is proportional to the normal stress, as we have assumed so far. It turns out that there are experiments that have shown that if normal stress changes rapidly enough, then friction shear resistance no longer is proportional to normal stress. Instead, it evolves gradually. So these experiments were developed by Prakash and Clifton in the 90s. They are the so-called pressure shear plate impact test, and they were developed for high-speed machining applications, so not earthquake mechanics context. And what they show is that here, when the normal stress has an abrupt variation, the shear stress has a delay. Eventually, it will catch up with the normal stress, but over a certain time scale. So now, if we look at close to the interface during our dynamic rupture experiments, due to the rupture impinging on the free surface, we will have a breakdown of the symmetry, which will induce rapid normal stress variations. It turns out that this is also relevant to the study of thrust faults, such as the one sketched here on the right-hand side. And so it's a very important problem to study for earthquake physics. So here I'm showing this field of view, which is taken from this region close to the free surface. And we have a rupture, scale here is in meters per second. We have a rupture coming from the bottom and going towards the free surface. As you can see, the rupture reaches and then the free surface, and then it's reflected. It was a super shear rupture, and it is followed by a trailing Rayleigh rupture, which is coming in a moment. It's just coming here from the bottom, and it reaches here the free surface. And these arrows indicate the particle velocity. It's amplified to show the motion. And again, this is just purely an experimental measurement. It's no modeling at all. So the idea is to follow now the shear stress with here scaling MPa. You can see that as the shear stress come from the bottom, it's nearly symmetric as it would be expected in the bulk. And then it reaches the free surface, and then there are pronounced reduction in shear stress. We have the trailing Rayleigh reaching with further reductions. If we look at the interface normal stress, likewise, before the rupture reaches the free surface, here's a snapshot, it's nearly anti-symmetric. Note that this black line indicates the level of pre-stress. So in black means unchanged stress level. So the stress is not changing. it's constant as it was in the bulk, but when the rupture reaches the free surface, then it becomes blue, which means like a reduction, and when the trailing really impinges the free surface, even a bigger reduction. So these snapshots show what we've just seen in the shear stress and in the phase normal stress. The most important thing to note here are these reductions. So if we take now a location very close to the free surface, and we track the evolution of shear normal stress versus slip, what we see is the classic evolution of the shear stress, but an evolution in the shear stress, which is, which has important features. For a rupture propagating in the bulk, as those that we saw earlier, we'd see like a constant level. So these reductions are such as that they produce like important variations in the friction versus slip. So now the idea is to use the same approach as earlier, where we want to fit the flash heating law and see whether it is capable of reproducing this behavior. And what we see is that it doesn't, because it can produce the weakening, but then this richness in behavior is not captured purely by the flash heating law. So we need to introduce the Prakash Clifton law, where when shear stress is no longer proportional to the normal stress, but it's proportional to a function psi of slip velocity and normal stress, and psi is given through its evolution. And so you can see that when psi dot is equal to 0, then psi is equal to sigma n, and then we recover Coulomb friction. But otherwise, we have an evolution, and it has a characteristic. There is a slip rate here, but there is also a characteristic evolution LPC, which is this characteristic evolution distance. So now the idea is to enrich the expression of shear resistance with this function psi, where we compute its evolution. Now the input in this evolution is the measure slip rate, the measure variation in normal stress, and then we fit for LPC, see whether we can find an LPC that can actually match the experimental measurements. And then we compare the ratio of measured shear to normal stress with the ratio of, with this ratio, where at the denominator we have the normal stress, but at the numerator, we don't have just, we don't have, so before we just had the friction coefficient, but now we have the friction coefficient times this function psi. And if we do that, then we obtain here the green curve. So we have black is the measurement, blue flash heating, and green is the new one. It's already a good improvement, but we are not quite yet there. So we have assumed here these parameters. Yes.
I just have a quick question, Vito, if you don't mind.
Sure.
If I remember correctly, Prakash Clifton is for when you have a difference in type of material, you are advocating this type of law. So what's the trigger, the reason you advocated this law?
Yeah, so Prakash Clifton is important and is relevant whenever you have a sudden variation in normal stress across the interface, as opposed to have a constant normal stress. Okay. Now, this happens in various settings. It happens when you have a bimaterial interface. It happens when you're close to a free surface, so you break down the symmetry, and in other circumstances. I will talk more on that later. But so the reason why you think about bimaterial interface is because a bimaterial induces a big normal stress.
Yeah. No, that I know. Okay.
But it's not the only case.
Okay. Thank you, Vito.
So the key thing is when the normal stress varies rapidly.
Okay, thanks.
Okay, so now we have assumed so far that FW and VW are kind of constant and obtained from the steady state analysis that I mentioned earlier. However, they were obtained by a steady state analysis that grouped tests obtained under various levels of normal stress. So now if we assume that really FW and VW also change with normal stress, and they can change both with the static, so we can do the same exercises I showed earlier at various levels of normal stress, and we can also introduce a variation with the actual level of normal stress, so with the dynamic stress change, then we can repeat the exercise and we obtain a much better fit of our experimental results. Now, the interesting thing about, and note here the separation length scale between the retained states L and the Prakash Clifton L. So the interesting thing is that we can use one test to train the friction law, and then we can produce tests under various loading conditions that have various slip rates driving the rupture. Now, if we use those slip rate histories as input to the friction law that has the same coefficients used to fit one experiment, we can fit all other experiments. So that's the important message, because it means that this law can actually be used to kind of in a predictive sense. So yeah, I've mentioned most of these points here, but yeah, implication for friction formulations, it's what we were discussing a minute ago, that it's, you know, it's very important to account for these types of friction laws in various problems, including thrust and normal force, when the symmetry breaks down and normal stress varies rapidly, but also when we have a slip-on rough, so non-planar interfaces and bimaterial systems. Okay, so now let me switch gears and go to the last part of my talk. Now, so far we have studied interfaces with analog materials, but if you are a geophysicist, you might say, this is not quite rock. But at the same time, I've showed you that using rocks is a little bit cumbersome, and well, it can be done, but it has some limitations. It doesn't allow as much flexibility. So here we have developed a hybrid configuration where we use an analog material here in the bulk, and we incorporate a layer of rock gouge material, which is quartz gouge in this case, so that we drive a dynamic rupture in the analog material. So the bulk count for the to provide the shear modulus, the right shear modulus and the right nucleation length scale. So we can get a dynamic rupture within a reasonably small length scale. And then once the dynamic rupture is well developed, then it enters the gouge layer and it propagates spontaneously. So we can study spontaneous rupture propagation in rock gouge on a small specimen with all the advantages of a compact setup with all the diagnostics that we've used so far. So we have a speckled pattern all within the gouge portion. And what we will be looking at next are images taken from within the gouge. So let me remind you what we saw for sub-Rayleigh rupture. So these are the same panels as before with the fold parallel velocity and fold normal velocity. So we have the rupture entering with these compressional and dilatational lobes and this signature in the fold normal component. So that's what it looks like. Now, what we will see next in gouge, we will see a supershear rupture entering, followed by a trailing Rayleigh rupture. So the supershear rupture will be arrested, I anticipate, and then we will see a sub-Rayleigh rupture, only it will be a zoomed out, because here we have a small field of view, so of about 16 millimeters width, and the field of view we'll see next is about 45 millimeters wide. So it's going to be a zoomed out version of these, and nothing else would be expected in HOMA light, but we'll see that there's a surprise that in gouge, something else happens. So same panels here. So here comes the supershear rupture. It is arrested. Here is the sub-Rayleigh rupture. You can see the signature here. Nothing else would be expected at this point, but here we see a rupture nucleating within gouge, propagating along the interface, and then arresting along the interface. And then at some point there are triggering attempts, and here a successful triggering attempt of a rupture that propagates and then arrests. Okay, so if we now focus on some snapshots here, so this is what we were looking at of a dynamic of a rupture which is dynamically nucleated within the gouge portion. So here is the slip rate that goes up and then propagates along the interface. And then at a location further ahead along the rupture, the same thing happens with the rupture nucleates and propagates. And we can also track the shear stress evolution. So here we have the remnant of the sub-Rayleigh rupture. And then here we have the big drop associated with this dynamically triggered rupture. And this is the kinematics of the last event that we saw nucleating at the right-hand side, right within the gouge. portion. Okay, so now I want to zoom out a little bit on the process, on the entire, the big picture of the entire process. What we do here is slightly different from the rupture I showed you earlier. So we have multiple initiation sites along the interface. So the specimen is first loaded to a set level of pre-stress. Then we have a sequence of ruptures. Then we crank up the load again, and then we have a second sequence of ruptures. And these two sequences are represented in these panels with spatial temporal plots, where we have the distance along the interface on the x-axis, and then we have time evolution on the y-axis. And then the scale here is in meters per second. So what we see in both cases is that we have initially an attempt of penetration by a supershear rupture, and then a trailing Rayleigh rupture, again, tries to enter the interface, but is arrested. So this black region is 0. So basically it's arrested, or nearly so. And then there are various attempts of nucleation, some successful attempts. And then here we have these dynamically triggered events that renucleate along the interface, which in this case are even more pronounced. So if we now focus on this second sequence, we want to analyze one by one these events. One way to analyze them is to track the slip profile along the interface. And so what we see is that we have a supershear rupture entering from the left-hand side, but as we were commenting on, it basically arrests. This is the trailing rupture that we saw arresting pretty much at the same location. And from about the same region where these two ruptures arrest, we have this rupture renucleating and then arresting at some point along the interface. And in the same region where it arrests, there is an attempt of nucleation, which is this bunch of green curves, but not very successful. And then we have this magenta curve, which is a successful nucleation attempt into yet another dynamic rupture. This is a very complex behavior, very different from what we saw with the analog material. So worthwhile studying gouge because it shows this richness of behavior, which is relevant to the material we want to study for earthquakes. Now, if we track friction and slip rate versus slip, one by one for these events, what we see is that initially we have this slip rate going up to nearly 2 meters per second, just below that. But that is, it only results into a really strengthening behavior of friction. So the other events are shaded, so I'm just highlighting one by one the events that I'm discussing. So next one is this trailing Rayleigh rupture, which has this important drop in friction. It is characterized by strengthening behavior, followed by dynamic weakening, and then healing or strengthening. And then we have this other event, which also is characterized by strengthening, weakening, and healing. But note the drop in friction. So we go from 0.35 to 0.58. So these are important changes in dynamic friction. Now, one thing to notice, for example, that for this second event, we go all the way to 0.15 with a slip rate of around 10 meters per second, whereas with Homalite, we could only reach 0.26 with 20 meters per second. So this indicates that slip is actually happening in gouge, and that gouge weakens in a more pronounced way. But now, if we focus on the strengthening part, so one possibility is that this strengthening is actually due to the direct effect of rate and state. It's legitimate interpretation. However, there are two things to note. One is that the direct effect happens at a very small slip compared to the weakening part, whereas here we have this strengthening occurring on a slip scale, which is on the order of about 15 microns, which is comparable to the slip scale of weakening. And then the other thing is that the increase in friction is 0.1, and it's much larger than would be expected by rate and state friction. In fact, some back of the envelope calculation would suggest like a increase of due to the effect due to 0.007, so much smaller. So this kind of points towards the behavior in gouge being a genuine strengthening behavior in terms of rate and state, and then followed by an enhanced weakening due to flash heating. So all of these observations in this friction and slip rate versus slip were done at one location along the interface, which is this one, X x1 equal to 5 millimeters. And so basically we picked up these 3 events. Now we move to this location of 40, where we won't see much of these 3 events, but we'll see most of the last event. And this is what we do here at the right-hand side. So not much of the first 3 events, but then this event is emphasized. And we can see that friction increases again substantially and then drops by large quantity. And this again points towards a pronounced 1/v dependence on slip velocity. So far we have observed like friction and slip rate versus slip curves, but now we can look at the same curves versus time. So there's time histories, and so for the first location x1 millimeter, we see these 3 events. We can see these big pulse here, and also for the location at 40 millimeters, where we highlight only the last event. Now we have the time history at 2 locations, but we can really produce nearly a continuum of time histories for all locations across the interface. So we can render a topography of these friction time histories. And this is done in this plot where we place the time history along this axis, and then the position along the interface along this axis going into the page. And then these shaded planes are cross sections done at the 2 locations that were studied so far, 5 and 40, reported on the right-hand side. And so we can also let this plane move to intersect the friction topography and trace various time histories. This is the one at 5 millimeters and so on. Few remarks here. One is that we have come a long way from simple linear slip weakening models, but even from written state. So there's a more complex topography which is obtained by combining written state and various other enhancing mechanisms such as flash sheeting that produce this richness in behavior. Now, what you see here is these peaks in red are locations where we have pronounced strengthening and where ruptures are arrested. And then the locations, the valleys in blue are locations where we have ruptures renucleated. And we have this pronounced weakening, and we have this runaway of dynamic events in gouge, which we do not observe for analog materials. So here we have the topography spinning around. This valley here is due to the initial trailing Rayleigh rupture. Okay, so let me make a few concluding remarks about this last part. So what we've seen is that these sequences of laboratory earthquakes navigate through gouge interfaces through an intermittent process, where we have arrest or nearly so, and then we have dynamic stressing, and then we have dynamic renucleation in these events. Now, what we have seen is that the gouge interface here behaves as a barrier because it tends to stop ruptures, as we've seen, with various attempts, and this is consistent with the strengthening behavior. At the same time, we have dynamic stressing due to the rupture propagating in other parts of the interface away from gouge, which sends dynamic stress waves to the gouge portion of the specimen, and this increases locally the slip rate, and this triggers dynamic weakening by the flash sheeting mechanism, and this leads to renucleation of ruptures. And this is a form of dynamic triggering. Our findings have important implications for the earthquake hazard assessment, because they indicate that you can have barriers in the earthquake propagation that you may think as unpassable and immune to the seismic slip. However, if you have dynamic processes such as they can increase the slip rate and trigger dynamic weakening mechanisms, then they can be penetrated by dynamic ruptures. Okay, so I will stop here, and I will be happy to take any questions you may have.
Thank you very much, Vito. Fabulous. I invite people to unmute, join me in thanking Vito out loud.
Thank you.
Really, it's fabulous comment. Okay, so please use the reaction button at the bottom of your screen to raise your hand. It'll be the easiest way to organize ourselves. And especially invite, everyone, but especially early career people to participate in the discussion, because yeah, lots of interesting things to discuss and to ask Vito to respond to. Men and Dream.
Yeah, fabulous talk, Vito. Thanks a lot. Are we surprised at all that friction doesn't stay low? Is it in these last plots that you show with the gouge? You just drop to this minimum level of friction for a very brief amount of time.
Well, so what was not clear from the beginning was whether gouge would, have a velocity weakening behavior in terms of rate and state, in which case it would allow ruptures to go through without arresting them. So if that would have been the case, then in these plots here, let me go back to these maps here. So then what we would see is that these events would propagate all the way through, as we see in Homalite. So the first surprise is that kind of these ruptures are arrested. Well, in this case, it's intermittent, but they're nearly arrested. And so the surprise is that gouge is a barrier here. And the second surprise is that because you have dynamic stressing, it's not a barrier full stop, but it's a barrier that can be breached if dynamic weakening gets activated. Now, if slip rate is high enough, then yes, we are not surprised that friction goes down to 0.15, because this has been revealed by other friction tests. But what was not clear was the complexity arising in dynamic rupture events.
I didn't mean so much that it goes down, but that it doesn't stay down, that it goes straight back up. Does
well,
that
because
teach us anything?
So right, because it's not sustained. It's because it propagates, and as you can see here, it moves around and it propagates, and more as if you will, as a pulse. So it tends to heal. Yeah. And so flesh eating has this aspect that may promote pulses. Yeah.
Yeah, please.
Hey, Vito, excellent talk. Thanks so much for all those cool experiments. A question regarding the last part with the gouge. Did you identify any localizations within there? I don't know how thick the gouge was, any localization, delocalization, shear bands, anything that you can tie together to these drops in friction?
Yeah, no, excellent question. So in a way, we cannot monitor that because you can see that we have so this gouge layer, and then we have a similar layer on the top, but then the specimen is closed, so we really only see at the surface, so we can't see through the gouge thickness because the gouge is confined. We expect, though, this localization to be happening in some way, and we expect that after localization has happened, slip to be concentrated along the interface, and the fact that that friction drops to these low values, much lower than we see in Homalite, is an indication that slip is indeed occurring in gouge in localized regions. Yeah, so it's kind of an inference, but unfortunately we cannot, observe it and see, we cannot look at these structures forming.
Okay, and maybe I missed it, but any quantification of the amount of dilation that occurs in the gouge during the rupture where it passes?
No, yeah, that's another important point, but no, it's something we cannot capture currently with this technique. So yeah, we have no indication whether most likely it is happening. but yeah, we cannot measure.
Okay, great. Thanks so much. It was really, really terrific.
Thank you.
Vito, it's Chris. Yeah, I really appreciate an incredible talk, and it's amazing the number of things that you guys have done. It's easy to have forgotten about some of them, but really impressive. So I raised my hand for two reasons. One is to ask a question, and the other is to really encourage people to participate in the discussion. I have a question about the different characteristic friction distances that you talked about. Do you have an intuitive insight about why there's such a big difference between the, let's call it the Rubinowitz or the Dietrich critical slip distance, and then the Prakash and Clifton one? You know, because if they're both related to contact junction dimension changes, how do you get this factor of 100?
Yeah, no, that's it's a very intriguing question. Well, it's difficult to answer in a way. So the Dietrich written state length scale is associated to the contacting asperity and to the history of evolution of the contact. So now the Prakash Clifton one is still linked somehow to the context because it's normal stress dependent, but in a different way, because I don't know, it's not associated to this constant distribution of normal stress, but to the variation of normal stress. So it has a dynamic component which is somehow not captured by the written state one. But I don't have a micromechanics explanation of the separation of length scale. We do find, that are orders of magnitude different, but micromechanically be interesting to go and explore, why, this separation comes, what's the source of this separation? Yeah,
and maybe that only happens for these more like dynamically propagating cases. I don't know, because
well, indeed, the dynamic component is a key part in here, because if the normal stress does not change rapidly enough, then the shear stress follows, and then the Prakash Clifton evolution does not come into play. So yeah, so there is an interplay between this length scale and the dynamics of the process. For sure.
Yeah, because for lower velocities where there's not dynamic interactions, then the normal stress dependent terms that sometimes can be thought of in terms of the Linker and Dietrich approach, yeah, those critical slip distances they're not terribly different.
Right.
Okay, thanks very much.